Now that we've looked at tangent lines to curves, we can use this tangent line to figure out what is called a linear approximation to a curve near a point. Let's have a look. So the idea is if we've got a function y equals f of x and a tangent line, which is this line here, at a point x equals a, then at some other point x, the function, which is a tangent line, approximately equal to the function at that point. So over some range, we can use this function L as a linear approximation to the function. Let's see this in action with a couple of examples. Let's look at the function 1 plus x to the power n near x equals 0. So we can work out what the linear approximation is if we calculate the derivative of the function at x equals 0. Well, the derivative is just n times 1 plus x to the n minus 1. So at x equals 0, this derivative is just n. And so that implies then that the linear approximation to 1 plus x to the n, I'll write with an approximation sign, is just 1 plus n times x. And this holds true for x close to 0. So we write this as mod x much less than 1. So in fact this is a really useful one to use. 1 plus x to the n is approximately 1 plus n times x. You'll see over and over again. Let's try an example with just some numbers in. Let's say you want to find, you have number 1.03 and you want the fourth root, say. Well, we can use this result by writing this in the form 1 plus 0.03 to the power 1 over 4. And since 0.03 is much less than 1, we can approximate this as 1 plus 1/4 times 0.03, and that equals 1.0075. If we compare this with the true value, which is 1.007417, we can see that this is a pretty good approximation. There's a number of very useful small angle approximations that come up a lot. These are sine theta is approximately equal to theta, for theta much less than 1. We can see this because f prime at 0, which is just cos of 0, is equal to 1, which implies that the linear approximation, which is f of 0 plus f prime of 0 of theta minus 0, is theta. Similarly, you can show that cos theta is approximately equal to 1 and tan theta is approximately equal to theta. So if you're dealing with a very squashed triangle, these come in really useful. There's a useful approximation to the exponential function near the origin. If I consider f of x is equal to e to the x, then that means that f prime at 0 is just 1. So therefore, for x near the origin, e to the x, since e to the x is equal to 1 at the origin, is just approximately equal to 1 plus x. And so for example, if I want to find or estimate the exponential of e to the 0.1, don't have a calculator to hand, I can say this is approximately equal to 1 plus 0.1, which is 1.1. And in fact, the actual answer is 1.1052. So again, a reasonable approximation. We'll see how to generalize these when we look at series expansions of functions. But for now, linear approximations are a really neat way to approximate a function. Let's finish off this subject by looking at the concept of differentials. This is really another way to think about the linear approximation. If I have a curve y equals f of x in blue here, and I choose a point on it, just some arbitrary point here, then if I move away from this point some distance delta x, the change in the function value is given by delta y here. And delta y is just equal to the function value at x plus delta x minus the function value at x. Now the differential dy is given by this distance in here. Where does this come from? Well, if I write down dy by dx is f prime of x, then that implies dy is equal to f prime of x times dx. This relates to differentials dx, which is this length here, and dy, which is this length here. In the limit that delta y goes to 0 and delta x goes to 0, we have the actual differentials dx and dy. We'll find this trick of rewriting dy by dx is equal to f prime of x and rearranging for dy equals f prime of x times dx very useful in the future.